Good afternoon, everyone. Thank you for giving me a chance to present our work here. And my topic is about proof of principle demonstration on modified ping-pong protocol on telecom fiber. As I am so amazing that the report before is achieves a so high bit rate, and I think maybe our result can be combinable with that result. Well, I would like to divide my presentation into three parts: a modified ping-pong protocol, experiment setup, and the results. Ping-pong protocol was proposed in 2002. It is the pioneering and inspiring work of two-way QKD protocols. Two-way means that Bob prepares and sends qubits to Alice, and Alice performs encoding operations to the incoming qubits and sends them back to Bob, who does the final measurements to decode messages. Here's a brief description of ping-pong protocol. At first, Bob prepares two qubits in the bare state psi plus. He sends one of the qubit termed the travel qubit to Alice, and store another one termed the home qubit locally. There are two working modes of this protocol. In the message mode, Alice performs a unitary operation I to decode the classical bit 0 or sigma z to decode classical bit 1. In the message mode, in the control mode, Alice measures the travel qubit in the basis z. Then she sends the measurement result to Bob. At the same time, Bob measures the home qubit in the same basis. Then he compares these two measurement results. If they are the same, then terminate the protocol. Otherwise, continue. In other words, the message mode is for serves the key distribution, while the control mode guarantees the security. Note that this protocol has no need of basis choices, so it is the so-called deterministic. While its security in LOSS channel has been challenged since being presented. Last year, our group proposed some modifications on this protocol. Here is the major. We proved the security against the connective attacks in noisy and noisy channels. This is the major modification. The original two encoding operation are expanded to 4, where I is expanded to I0 and I1. Sigma z is expanded to Y0 and Y1. Actually, I0 and Y0 are equivalent to I and sigma z respectively. While due to the vacuum states, the I0 is different from I1. Similarly, Y1 is different from Y0 is different from Y1. This simple but nice demonstration introduces the phase randomization to Eve's system. So limited the achievable information for Eve. Details about the security proof is you can see this paper reported last year. The final security rate can be estimated by in equation below. Here, S denotes the channel's binary entropy function. P01 means the probability that Alice measures 0 or while Bob measures 1 in the control mode. Other probabilities have similar meanings. Eta means the transmission efficiency of the backward public channel, not the forward. E means the error rate and the message mode. Here is the experiment setup. Part 1 denotes the polarization entangled photon source based on type 2 PBKDP and polarization Sagnac interferometer. Part 2 denotes the bare state measurement, which contains a beam splitter followed by 2 polarization beam splitters. Part 3 serves the message mode. Is that actually another polarization Sagnac interferometer. Now, Part 4 denotes the setup for control mode. In this simple prototype demonstration, we perform the message mode and control mode separately. The travel photon is sent to Alice through a 10-meter fiber link. Then it is sent back through the same fiber. The home photon is delayed by the 45-meter fiber. Finally, these two photons, will meet at the BS at the same time. In part 1, the generated polarization in tangled photon source has the degenerate wavelength of 1,560 nanometer. Under the continuous pump power of 160 milliwatts, we achieved about 1,000 coincidence per 10 seconds. And we achieved raw visibilities of 96% in the H wave base and around 99% in another base. If you want to know more about the polarization stack-and-hack configuration, you can see this paper. And our paper about this source is under review now. So I did not give more details about it, because this is not the important part. In part 2, consider the case that there is no encoding operation. What is the initial two-photon state received by BSM? If it is psi plus, then the gated detectors DV1 and the detector DH1 may click, then generate a coincidence. Or if it is psi minus, then DV1 and DH2 may click, then generate a coincidence. The coincidence rates are denoted by CV1 CH1 and CV1 H2. The ratio between them are denoted by R. Ideally, psi plus corresponds to the case that R is infinite, while psi minus corresponds to the case that R is 0. Finally, R achieves the 2.6% through minimizing the path length difference between the travel and home photons. Additionally, a value of CV1 H2 achieves its just achieves half its maxima with the path length difference out of the coherence length. So it has high reliability of receiving psi minus as the BS initially. For the encoding operation at the Alice side for the message mode, actually the travel photon is guided to another polarization stack-and-hack interferometer. Here is the working principle. The H state of the travel photon will propagate clockwise in this loop, and its phase modulation voltage is V1. While its V state will be rotated by the 90 degree Faraday rotator to H, then propagate counterclockwise in this loop, and its phase modulating voltage is V2. Operation here can be described by this equation. Obviously, F can cover the 4 encoding operations defined by the modified Ping-Pong protocol. And the two photon state received by BS will be changed from psi minus to another two photon state determined by the phase modulating voltage difference. Here is the encoding table determined by V1 and V2. And the corresponding operation and error weights are given. For the operation pair of I0 and I1 or Y0, Y1, the error weights are balanced. And through scanning the phase modulating voltage difference, V1 minus V2, we see that the evolution curves of CV1, CV1H2 and CV1H1 match the theoretical equation here very well. And the raw visibility raw visibilities achieve 87% and 88% respectively. Finally, for the loss tolerant test, we insert two variable attenuation plates into the free space to simulate the increase of the fiber length of the forward or backward public transmission channel. And to do the worst case analysis, the initial two-photon state received by the BS is reinitialized as the psi plus, and the triggering rate frequency of DV1 is reset to 90 megahertz to achieve higher coincidence rate. Additionally, the encoding operation is fixed at I0, I1. Sorry. Here is the final result. The red lines and the points correspond to the absolute secure key rate. It equals the multiplication between my raw key rate and R, where R means the bits per coincidence. The raw key rate represents the overall coincidence rate, where the eta just notes the equivalent fiber link simulated by the variable attenuation plane, and its loss is just half of it. Due to the two-way transmission, its loss is just half of it, this plane. Finally, we see the key rate is so low. That's because of the low injection rate of the entangled photon source. And the communication, a transmission fiber link can be up to 24 kilometers. In conclusion, in this simple demonstration, we verified the feasibility of modified ping-pong protocol over lossy telecom fiber channels. It is the first demonstration of secure entangled-based deterministic QKD over lossy channels, and it is also the first demonstration of ping-pong protocol on telecom fiber. Actually, it seems like the telecom fiber is just the only candidate for this kind of protocol, because the free space in the secure, if we use the free space channel, the secure row of bulb will be very big to storm the local qubit or photon. Second, we build a high quality entangled photon source at the generate wavelengths of within the telecom band. Actually, through adjusting the temperature, we can change the degenerate wavelengths, and the bandwidth is about several tens of nanometers. Third, we designed a polarization second interferometer for coding. It has very low loss, stability, and compactness. And make use of the two-way transmission, we reduce the difficulty and the cost. I want to say that the modified ping-pong protocol may have no clear potential use or applications or advantages over the BB84 or current other protocols based on the multi-photon source like coherent recoherent process. But I think it is still a meaningful step toward exploration of two-way or deterministic QKD protocols. Thank you very much.
Okay, questions?
Thank you so much. So let me confirm that transmission distance is 10 meters now.
Yeah, just 10 meters.
And what prevents you from increasing the distance?
Pardon?
What prevents you from increasing the distance?
Let's see, I just used
What's the obstacle to increase the distance?
I used the variable attenuation planes to simulate it, not just the real long fiber to do the experiment, just a simulation. So it's a table experiment.
Okay, so what is the future plan?
Future
Future plan
plan. Oh,
from the viewpoint of to increase the distance.
this is how to see the biggest limitation is comes from the brightness of the entangled photon source. But even we increase it to a very high level, but I think it's not still so practical. It's just some experimental exploration.
Experiment. Okay. Thank you so much.
Thank you.
Any more questions? I can't see any. Well, I think that's taken us back on time, so we'll just thank the speaker one more time.